This one is forward.
This one's forward, and then that's the laser.
Is Joseph Dyson. He is going to talk on the gravitational wave reflectivity from ultralight boson cloud.
Yeah, so today I will be talking about a dark matter candidate, the ultralight boson, and how we might be able to probe and constrain the mass of this candidate particle, considering the reflectivity, the echoes essentially of gravitational waves in a system of a black hole surrounded by a cloud of ultralight bosons. Okay, so to begin, I'll give a roadmap of where we're going to go today. We'll start off by discussing what ultralight bosons are in the first place, as well as how the process of superradiance can lead to essentially a cloud of these ultralight bosons encircling a black hole. We'll then talk about a number of possible ways for probing and constraining the mass of the ultralight boson, presenting those ways. And then I will focus on talking about this signature of an echoes effect in the ultralight bosonic cloud, where this cloud essentially causes gravitational waves to bounce back and forth between the angular momentum barrier of the black hole and a potential from this bosonic cloud, resulting in an echo-like gravitational wave at our detectors. And then I'll end on some conclusions. So to begin, we should answer the question, what exactly are ultralight bosons? So as I mentioned earlier, they're a dark matter candidate. Typically, we talk about scalar ultralight bosons, although there are also vector ultralight bosons. Their mass range is quite small, typically on the order of 10 to the negative 22 electron volts, but it can vary substantially, going sometimes as high as 10 to the negative 10 electron volts, or several orders of magnitude lower as well. And when an ultralight boson is near a Kerr black hole, a spinning black hole, there's this process of superradiance where if the boson frequency here, omega b, is less than the angular velocity at the black hole horizon times the azimuthal quantum number, then there will essentially be a negative energy, an angular momentum flux from the black hole to the bosonic cloud. This essentially extracts angular momentum and energy from the black hole and deposits it into the bosonic cloud, reaching up to roughly 10% of the total mass energy of the black hole. And if we have a massive boson, so this boson has some sort of mass, then it can result in a fairly stable bound state where we have this surrounding bosonic cloud around this dense black hole. And I think there's a really nice analogy here with an atom where we have this black hole nucleus, you can think of it, surrounded by this cloud, this bosonic cloud, just as we might have an electron cloud in an atomic model. So this is a cute picture from a paper another student at CUHK wrote. Here we have a supermassive black hole with this immense bosonic cloud surrounding it. I think this is a nice picture to sort of suggest what we're talking about here. You can focus on the black hole and the cloud. Please excuse Lisa. It got a little too close to this black hole, it seems. So how can we probe the ultralight boson? There's a number of processes. The first is in the stochastic background of gravitational wave emission. If these bosons exist, they will have some energy flux as gravitational waves essentially flux from the bosonic cloud outwards. And so we can detect this in some sort of stochastic background in our detectors. So for very high ultralight bosons, this background is quite large, and so this can constrain a boson mass from above. In addition, we can consider possible holes in the parameter space of spin and mass in black holes. As it turns out, the timescale on which these bosonic clouds and black hole systems are stable varies depending on different possible spins and masses for black holes. So in certain ranges of the spin mass parameter space, these systems will not be stable for very long. They'll radiate away very quickly, and this will result in some holes in our spin mass plane. So if we are able to see and identify these holes, that can be a signature of the ultralight boson. Now our focus here is a consideration of the potential of these ultralight bosons in the wave equation, how these bosonic clouds can result in some sort of echo signal, which I'll get to later. So to start talking about echoes, I'll just talk about sort of our typical model in discussion of echoes in the context of gravitational waves. To resolve a number of issues in the interaction of quantum effects and gravity, some people have proposed various exotic alternatives to black holes, where instead of having an event horizon out of which nothing can emerge, we might have some sort of membrane or firewall around the Schwarzschild radius of these compact objects. Then, if we imagine some sort of gravitational wave emission beginning at the angular momentum barrier around this compact object, of course, a substantial amount of that will propagate outwards directly and be detected by our detectors as an initial signal. However, some of it will also be directed inwards towards this sort of boundary around the Schwarzschild radius and can reflect off, hitting again the angular momentum barrier, in which case some of it will transmit, reach our detectors, but some of it will then again reflect backwards, and so on and so forth, resulting in an initial signal plus a series of echoes of the initial signal separated by some time t echo. And our question here is, considering this black hole and bosonic cloud system, can we identify a similar effect, and might that effect be a possible probe of the ultralight boson mass? So I'll now get into talking about how we go about calculating and identifying this echoes effect. We begin by considering the wave function for the L equals m equals 1 mode of the bosonic cloud, generally the most stable mode for the wave function of the bosonic cloud given here. Of course, the m here is just the black hole mass. ms, as I mentioned earlier, is the total mass of the bosonic cloud extracted in the superradiance process, and can range from up to about, say, 10% of the total mass energy of the black hole. Probably the most important thing about this wave function, though, is it's dependent on mu, which is proportional to the very mass of the ultralight boson. And it is this which will serve as a proxy for identifying or constraining the boson mass. We can then construct a stress tensor given this wave function in the case of a scalar ultralight boson shown here. And then our question at this point is, how does this stress tensor modify the gravitational waveforms in our black hole bosonic cloud system? So to answer this question, we turn to the Tokarski equation, which we heard about a little bit yesterday. Now, the Tokarski equation is this very convenient, beautiful differential equation considered from a perturbation of the curvature rather than a perturbation of the metric itself. We then get this nice master equation for the gravitational waveform, which works quite generally in any sort of Kerr black hole or Schwarzschild black hole system, alongside this source term on the right-hand side, which in the case of a vacuum, we set equals to 0, but in the case of some stress tensor, is fairly complicated. So just be aware that this T contains a lot of information in it. Now, to get our stress tensor into the language of the Tokarski equation, we first project it onto our null vectors, which we use in the Newman-Penrose formalism to construct the Tokarski equation, as shown here. Probably the most important thing about this is its dependence on psi4, which contains the gravitational waveform itself. And as you'll see, that results in this basically acting as a potential. Now, we assume that our waveform can be decomposed nicely in terms of spherical harmonics, harmonic in time, and then some radial function, let's call it R. If we consider the L equals m equals 2 mode, the dominant mode for gravitational wave propagation, and then we get this language fully in the language of the Tokarski equation, such that we can actually put it back into the master equation by applying a series of differential operators and hitting it with several factors of R. Rho here, I should note, in the case of a Schwarzschild black hole, is 1 over R, which is what we're working with here. We further assume that the radial solution should be some sort of spherical wave, as we might imagine. And we make the ansatz that to leading order, the derivative with respect to radius of our radial solution should be dominated by this harmonic dependence in radius. It should be dominated by that oscillation. Now, going forward, the beautiful thing about the Tokarski equation is that the radial equation and the angular equation decouple. In doing that, we finally arrive at our wave equation for the black hole bosonic cloud system. It's much like the original case of the radial equation one normally gets from the Tokarski equation, where we have this omega squared factor, this effective potential, the Schwarzschild potential, and then the important thing here, though, is that Q of R is this extra contribution from the bosonic cloud. And the reason this happens is that rather, as I mentioned earlier, our stress tensor carried with it a factor of psi 4 itself, like essentially carrying with it this radial function R here. So our stress tensor, rather than acting like some sort of inhomogeneous forcing term in our wave equation, acts as a potential because it carries that factor of the waveform with it. Now then, our question at this point is how can this potential affect the gravitational waveforms? Can this come with some sort of echoes-like signature? And so to give you a model of what we're thinking about here, I've drawn you this little cartoon showing what's going on. So we have this angular momentum barrier at about R equals 3 times the mass of the black hole in the units we're working with. And then we have this peak in the bosonic cloud potential, Q, occurring at a large distance outside of the angular momentum barrier. If we imagine a gravitational wave that initially propagates outwards from the angular momentum barrier, of course, we expect that most of it will transmit through the angular momentum, the bosonic cloud potential and reach our detectors. However, some of it can then reflect off of the peak of the bosonic cloud potential, hit the angular momentum barrier again, and then reflect once more, resulting in our first echo, and so on and so forth for a second echo, third echo, etc. And as it turns out, this time delay between the echoes is actually dependent pretty closely on the value of the ultralight boson mass. And in this way, detecting an echo can be some sort of probe of this boson mass. Now, if we want to really understand our waveform model here, we need to compute what we call the reflectivity, which is essentially the proportion of a waveform that reflects off of our potential, off of our bosonic cloud potential. So we consider at first an analogous situation. Here, we're considering an ingoing wave starting at spatial infinity. So some sort of gravitational wave coming in from very far away. In which case, as you might expect, we have this boundary condition of an ingoing wave at infinity. And then also, we're still talking the language of black holes, so naturally we have an ingoing boundary condition at the event horizon. The important thing here, though, is that some of that ingoing wave reflects off of our bosonic cloud potential and comes back out and is outgoing once more at spatial infinity. And then we can apply this in a Dyson series approach, essentially a geometric series and factors of this reflectivity, which in itself is a geometric series in the bosonic cloud potential, as shown here. I haven't written it all out because it's quite unruly and complicated, but the general idea here is that each of these psi ends are acting as essentially as a geometric series in this reflectivity in this bosonic cloud potential. Now, the bosonic cloud potential is quite small, and so we just consider it to first order in that equation I showed earlier. In which case, we have a nice little integral which approximately captures the reflectivity due to the bosonic cloud, which we can compute numerically. We integrate out from, we have to choose carefully where we're integrating here in order to sort of capture the features of the bosonic cloud peak. So we integrate out from 3m, essentially the light ring of the black hole, out to what's proportional to 1 over mu cubes, where mu, as I mentioned earlier, is that ultralight boson frequency in itself related to the ultralight boson mass. And the reason we go out to 1 over mu cubed is so that we can capture the peak of Q, which happens pretty consistently at 1 over mu squared. So we do this numerically, varying mu, varying our parameters for the ultralight boson mass, and then varying the frequency of our gravitational waves. We get plots that look like this. So here I've just fixed the frequency of the gravitational waveform at the 2-2 quasi-normal mode, and I varied mu and calculated the reflectivity for different parameters of mu. Probably this serves as a good check on our calculations, as we see that for very small mu, the reflectivity goes to 0. So essentially, if the boson mass is 0, there's no reflectivity, exactly what we should hope to see. However, the reflectivity is dominated by a factor of mu to the 8th, so it grows very quickly as the ultralight boson mass increases. Then I've also now in this plot fixed mu, fixed the ultralight boson mass, and calculated the real part of the reflectivity for a variety of frequencies. Now the first thing that might jump out to you here are these white parts. They look bizarre, but do not fear, that's just a result of the reflectivity in these regions being outside of the bounds of the contour plot. If you zoom in, they're much cleaner. And with our reflectivity, we can now go forward, calculate essentially what our echoes model should look like, as this reflectivity controls both the phase and the amplitude of waveforms being reflected and transmitted at the barriers of the bosonic cloud peak. You should note that a negative reflectivity essentially amounts to a phase shift, and the magnitude of the reflectivity controls the proportion of the gravitational waveform that travels outwards or reflects. Now, our future work going forward is to understand this in the context of a time domain waveform. So be able to construct a phenomenological model for an echo effect, bouncing not between that earlier slide of some boundary condition around the Schwarzschild radius, but rather between the two peaks of our potential, the angular momentum barrier of the usual potential and the bosonic cloud potential. And then we need to understand fully how this potential changes our echo model. So the echo model can be a little bit simpler in the clean situation where we're just talking about the reflection boundary condition at some alternative black hole candidate. But in our case, bouncing between two potentials can be a little bit more complicated. Then we hope to take our phenomenological model and actually be able to draw constraints on the possible values of the ultralight boson mass using LIGO events. And also, we need to consider degeneracy, so ensuring that there are no other sort of physical candidates, physical theories that could result in a similar effect. And then I think going forward, it would be good to think about other possible signatures we should be able to expect from this bosonic cloud. And that concludes my talk.
Question and comment.
Yeah, this eco thing, the boundary condition generally used, it's generally very phenological, right? You use, instead of ingoing boundary condition, you use some absorbing boundary condition. So suppose one uses a mix of that, ingoing plus some fraction ingoing and some fraction reflecting.
I should be careful. When you're talking about boundary conditions, are you talking about boundary conditions at
The inner boundary and where
the Schwarzschild radius?
Schwarzschild radius, yeah.
Okay, yeah. So we're actually not. I mean, I think one could go forward and probe what sort of a signature of a gravitational waveform with some sort of reflection boundary condition might be in that case. But right now, we're not actually considering any sort of alternative candidate for a black hole, let's say. We're just right now focusing on the pure ingoing boundary condition. But I think there's been some papers that consider both some sort of reflectivity effects, say from some potential, as well as considering some boundary condition at a black hole.
It's a free parameter in the model of how short it out. It's a free parameter reflectivity.
Yeah.
That they fit from the data.
They fit from the data.
Yeah, it's not put in to be 1 or 0.
From the QNM data.
Yes. Yep. Well, more than that, but yes.
Okay, it's an interesting idea, I think. But you assume some gravitational waves coming out, but isn't there such kind of strong gravitational wave from just rapidly rotating black hole with this cloud?
Yeah.
So I wonder what kind of gravitational wave source you are assuming.
Yeah.
The end states both merging or just...
Oh, sorry, what gravitational wave source we're assuming?
What makes such a strong gravitational wave in this situation with a single rotating black hole with cloud?
I see. So I think we're right now focusing on sort of the ring down stage of a black hole. So black holes have merged, there's some ring down emission, and what does the waveform look like in that? So for a single black hole, essentially. Does that answer your question?
Yeah, okay, that helps.
I noticed that. I noticed that your peak of your boson potential is outside the angular momentum boundary, whereas for the Abshorty model is inside.
Yeah.
Is it possible to put the peak of your bosonic potential inside the angular momentum barrier, or is that just not possible mechanically?
It might be possible, but I think some of the assumptions we've made about deriving all this are dependent on having a relatively small ultralight boson mass, and I think the peak of that potential, in order to be between the angular momentum barrier of the black hole and the event horizon, needs to be, I think, large enough that some of these assumptions might not work.
Could you show me the page 16?
The what?
Page 16.
16? Yeah.
So what is the unit of mu?
Okay. So in the units we've chose where the Newton's constant and the speed of light are 1, mu carries a factor of inverse length. So, but I've chosen m. This is essentially the product of the black hole mass times mu. So setting the black hole mass equal to 1, then mu is equal to 0.1 here. This is not, I should note that this is not actually the ultralight boson mass, it's the ultralight boson mass up to a factor of Planck's constant.
So mu equals 1 means mu, mu equals 1 over n.
Mu, m mu, at this point, m times mu equals 0.1.
Mu also carries the dimension of mass, right?
Yeah, yeah.
And n also carries the dimension of mass.
No, sorry, mu carries a unit of inverse mass. Yeah, yeah, yeah. So m mu is dimensionless. Yeah.
Could you show me the definition of mu?
I think it's pretty far back here. Here. It's the actual boson mass divided by h bar. So it's the boson mass up to a constant.
Then mu carries the dimension of mass.
I think in these units, the Planck's constant carries a factor of length squared. Yeah.
Okay. And the 39th question is that when we do quantum mechanics reflectivity calculation, we just assume some plane waves and matching boundary conditions.
Yeah.
And what is the difference between this method and your two code?
That's a really good question. I think the advantage of the Dyson series we're working with here is that it's a geometric series in the reflectivity, so it's pretty easily isolated, at least to the first term. But I think there's also, I've seen definitely ways for computing the reflectivity of the angular momentum barrier in terms of, I think what you're describing, where they've got matching boundary conditions on each side of sort of the scattering potential and then computing the reflectivity from that. So I think it's possible to do it in a similar way. Yeah.
And the last question is that the page 16 figure.
16?
So basically, reflectivity is, for me, is quite small value, has quite small value.
Yeah.
Basically, the echoes amplitude from the original source gravitational waves is suppressed by that factor.
Yeah.
So, is it possible to, in practical sense, is it possible to observe any binary black holes or some black hole and ultralight bosonic cloud has made some observables from LIGO or Dyson in the near future?
Yeah, so essentially the parameter space of the boson mass we can constrain with this approach, if I'm understanding that correct.
Yeah, in near future, we can compare the black hole and ultralight boson system as binary black hole system. We can make some analogy.
Mm-hmm.
And in my night guess, these two systems make some similar amplitude.
Mm-hmm.
But LIGO or Lisa can observe only the first signal first emission signal.
Right, yeah.
Only. So if the second echo, first echo is suppressed by the factor, then it's really hard to observe.
Yeah. Yeah. So, one helpful thing here, though, is that because the reflectivity scales as mu to the 8th, even if it's quite small here, it can grow substantially for not that big of a change in mu. And so in which case the reflectivity could be probable potentially by near soon to be made detectors. Yeah. Yeah. Or at the very least, we can draw up some constraints as of right now and then maybe make more competitive constraints later on.
Any other question?
Okay, let's thank
next speaker is Yeong-Bok from NIMS. He is going to talk on the gravitational radiation driven capture of two black holes.
Can you hear me? Hello, my name is Yeong-Bok and I'm a postdoc at the National Institute for Mathematical Sciences in Korea. And today I want to talk about the gravitational radiation driven capture of two black holes. As you know, black hole binaries are the main sources of gravitational waves. They have detectable frequency and strength for current interferometric gravitational wave detectors. And they have predictable waveforms. So we can calculate their waveforms by hand or by computer. And their waveforms are divided into three phases. First is in-spider phases. And second is merger phase. And the third is ring-down phase. And binary black hole can be formed in the field environment. Stellar binaries can be transformed into the binary black hole if they endure the supernova explosions. And second condition formation is in the cluster. They can be formed in the dynamical regions. So today we will see this kind of topics, dynamical formation. Let's see the dynamics in cluster. Self-gravitating system like a cluster or even stars experience this core collapse. Even though their initial center density is low, but time goes on, their center density becomes higher and higher. This is called core collapse. And we should think of mass segregation. More massive components sink toward the central region more quickly. So black hole is a massive component in the cluster. For example, there are many massive stars in the cluster, but massive star lifetime is very short, so they changed into the black holes. So the average mass of the stars in, for example, global cluster is less than 1 solar mass, like a 0.5 or 0.7 solar mass. So typical mass of black hole is around 10 solar mass or more massive, heavier than that. So black holes are the massive component in the cluster. So they sink toward the central region quickly, and they form the high density central region of the cluster. There are many black holes in the central region, and in there black hole binaries can be formed through the different kind of scenario, and through the interactions the black hole binaries can be hotter and hotter, and finally they are ejected. Most of them are ejected from the cluster, and they merge by emitting gravitational waves. First scenario is Threebody process. In the central region of the cluster, three black holes can interact with each other, and among them, two black holes can make a binary black hole, like this. This is we call this Threebody process, and sometimes it changes its partner. For example, 1 and 2. Mass 1 and mass 2 was coupled, but through the very chaotic interactions with 3, 1 divorces 2, and 1 get married 3, particle 3. The other kind of formation scenario is gravitational radiation driven capture, and many people say the word the gravitational wave capture. This is just two-body interactions, And through the very close encounter, the unbound orbit can be changed to the bound orbit by emitting gravitational waves. The condition for the gravitational radiation capture is energy radiation is larger than orbital energy. This is one example. Here, red line is the orbit of the Newtonian. This is equal mass cases, but we just draw the relative orbit. So we fixed one particle and one black hole, and we just saw the other orbit. And initially, it has a hyperbolic orbit. So in the Newtonian, the other black hole goes out and never return. But if we consider the gravitational radiations, then it follows like a blue line orbit. Goes out and return again, goes out, return again, and it can be captured by each other. Let's see the gravitational radiation capture. For the study of gravitational radiation capture, many people use the parabolic approximation because it's hard to. We want to find the marginally capturing hyperbolic orbit, but it's hard to get the initial conditions of marginally hyperbolic capturing orbit because we don't know how much energy will be radiated beforehand. So, parabolic approximation. Hyperbolic orbit has a similar path with parabolic orbit around the pericycle, where most gravitational waves are radiated. So we boldly assume that gravitational radiation from hyperbolic orbit is the same with that from parabolic orbit. By assuming that, we just calculate the orbital energy of the marginally capturing hyperbolic orbit from the parabolic orbit simulation. For example, radiated energy is 0.01 in parabolic orbit. It means the hyperbolic orbit with the orbital energy 0.01 can be captured because it will radiate this amount of energy. And critical impact parameter for gravitational radiation capture can be calculated through very simple formula. Here E is orbital energy, and mu is a reduced mass, and V infinity is a velocity at infinity, and L is the angular momentum. And with these formulas, we can calculate the critical impact parameter with the energy and angular momentum. And here, energy is orbital energy of the initial hyperbolic orbit, but we can change this energy with the we can substitute with the radiated energy from the parabolic orbit if we adopt the parabolic approximation. And for the gravitational radiation capture study, the first approach is we can use the Newtonian orbit for that. In the very weak encounter, the orbit is almost the same with the Newtonian orbit. So we draw just Newtonian orbit and calculate the gravitational waves following that with the quadruple formula. And Peters 1964, according to Peters 1964, the time average of energy emission rate of eccentric orbit can be expressed like this. And the time derivative of the eccentricity can be expressed like this. And we can see here the change of the eccentricity. For example, initially it has a very high eccentricity, close to 1. But as time goes on, the eccentricity decreases, and they have almost circular orbit. So this is called circularization, and so most gravitational waves detectors adopt the consider the just quasi-circular orbit for the black hole binary black holes. And for parabolic orbit, we can calculate the radiated energies with this function of RP. RP is a pericenter distance, shortest distance between two black holes. And next approach, second approach is we can consider the post-Newtonian equation of motion. For the strong interactions, the orbit is not same with the Newtonian, so we should calculate more accurate orbits. And for example, up to 2.5 post-Newtonian terms, the equation of motion can be expressed like this. And here A and B are given like this. And we can solve this simple equation and we can obtain the orbits. And in this equation, this is just up to 2.5 pn, but we can add 3 or 3.5 pn like that, and we can add spin-orbit coupling or spin-spin coupling like that. So this right panel shows some kind of evolution of eccentric binaries from Dr. Hong. And first is a semi-major axis, next is eccentricity. Initial semi-major axis is 10 to the minus 4 astronomical unit, and E is 0.9. And as time goes on, the semi-major axis and eccentricity decreases like this. And this graph I draw by myself because he didn't supply this picture. This red lines are the orbit of the first method. So here black hole starts and goes elliptic orbit, but they radiated energies, so their semi-major axis and eccentricity decrease a little bit. So their next orbit is a little bit inward. So this is the first method. And second method, if we consider the post-Newtonian equation of motion, then its orbit is like this. This shows us a kind of precession like that. In that case, second method, according to the second method, as a major axis and eccentricity decreases more quickly. And we can use this method to the GR capture. For example, I showed you this orbit, and here these blue lines are drawn by the second method. And third approach is numerical relativity. It solves the Einstein's equations by numerically, and it does not consider the black hole as a point mass. It means it can describe the horizon shape like that, and it can consider the spin effect, and it can be used very strong encounter, or even the merger and ring down phases. But the shortcoming is it's a very expensive calculations. Here I show you several features of GR capture. Left panel shows the expected distribution of the semi-major axis and eccentricity and merging time in the Milky Way-like galaxy center. And as you can see here, eccentricity log 10 or minus E has a peak at almost minus 4. It means eccentricity is 0.9999. So you can see here, CAPTCHA can make a very highly eccentric orbit. And the right panel shows the here color is eccentricity at 30 hertz. So as you can see here, some of them can have some eccentricity, not negligible. So we can say that the binary black holes that is formed from the CAPTCHA can have sometimes eccentric merger. And this is the other example of the eccentric orbit that is formed through the gravitational radiation capture. And here A and semi major and eccentricity is from this distribution. Most typical value is semi major axis 0.153 astronomical unit, and eccentricity is 0.99989. And here we can see this kind of very elongated orbits, and we can expect this kind of sporadic burst type of the gravitational waves. Of course, in the final stages, we can expect the very continuous waves. And the other kind of waveforms is merger ring down without signal. This orbit is a direct merging orbit. So this does not have in-spiral phases. So their waveforms are their in-spiral waveforms are not shown. They have just merger and ring down phases. And the other kind of waveforms are from the very restricted conditions in zoom and wall orbit. You can see here the orbit is very two black holes get close and go out, and again get close. So we call this kind of orbit as a zoom and wall orbit, and its wave is like this. It's like a combination of burst orbit and merger ring down orbit. And upper panel of this figure shows the orbit with changing the initial angular momentum. So if initial angular momentum is sufficiently large, they show this kind of flyby orbit. But as we decrease the initial angular momentum, its orbit changed to the direct merging orbit. And this kind of waveforms we can expect. And this right panel shows the radiated energies. Let's just see the black lines. Black lines are for the equal mass cases, and the right part of this peak shows x-axis means initial angular momentum, and right part of the peak is from the flyby orbit, just one encounter, and left part is from the direct emerging orbit. And as you can see here, the most gravitational radiation are around the boundary between flyby orbit and direct emerging orbit. And black hole orbits can be affected by the spins. This shows the orbit. Black lines are low spinning cases, and red line is anti-aligned spin. It means two black holes have anti-aligned spins to the orbital angular momentum. And blue shows the aligned orbits. And you can see here the anti-aligned black holes can have more wound orbit. And it means anti-aligned cases, it has a larger cross-section for gravitational radiation capture. Yeah, black hole binary can be formed by very close encounters with emitting gravitational waves, and highly eccentric orbit can be formed from GR capture. And there are three kind of approaches for GR CAPTCHA: Newtonian orbit, post-Newtonian corrected orbit, and numerical elastic simulations. And we can expect this kind of new kind of waveforms, sporadic burst, merger ring down without inspire, and zoom and all of it like that. Yeah, thank you.
Comments?
On your plot where you compare the post-Newtonian corrected orbit to the Newtonian orbit,
Yeah.
where you have the perihelion precession, is that post-Newtonian corrected orbit, is that just the leading order post-Newtonian correction, or have you added many orders?
For the orbit, up to 2.5 post-Newtonian.
Up to 2.5?
Yeah, and following that, I just use the quadruple formula.
So do you know that because the change from the Newtonian orbit to the post-Newtonian orbit is very large. Is there an argument for why higher order post-Newtonian corrections will not change it more? I mean, are you reasonably confident that your post-Newtonian corrected orbit with those parameters that you used is close to the true GR answer?
Yeah, actually,
Or is that why you
we are
use
doing
numerical
some
versus-
comparison with post-Newtonian or numerical relativity. And actually, if we add more higher order terms like a 3pn or 3.5pn, the orbit changes. As for example, this is a variation of same major axis and eccentricity. This is a Newtonian orbit. This is a 2.5 pn orbit. But I tested 3.5 pn, then it goes to this direction. So 3.5 pn cases between Newtonian and 2.5 pn. So, yeah, I don't know how many post-Newtonian terms we need, but
So for these parameters, you haven't seen then any kind of convergence of the PN series. It's jumping around between the 0 PN and it's all over.
yeah, I haven't, but I can do that.
So this is what you need the numerical relativity for. It sounds like you don't really trust this thing.
Well, he has NR results as well
Yeah.
for the orbit.
Sorry, he has NR results for the
Oh.
orbit.
Yeah,
So he can check it against the NR results.
that's right.
Yeah. Actually, this is these are drawn by myself, but the problem is, as you know, numerical relativity is very expensive, so we cannot test very far interactions. But close encounters NR gives the other results, deviations from the post-Newtonian episode.
Any other question?
When you were talking about the three-body interaction
Yeah.
in clusters,
Yeah.
I thought I heard you say that the majority of binaries that are formed by three-body interactions in clusters will be ejected from the cluster.
Yeah.
Is this true? Does this mean that most binaries formed in clusters are floating around in the universe, not bound into clusters that are all over the place?
Yeah, actually, several years ago, I did kind of n-body simulations for that, and many n-body simulations support the very hard binaries can be ejected finally from the global cluster. But nowadays, several people says there can be some black hole binaries inside the cluster. Yeah, that's a controversial.
Would you show the waveforms for encountering two bodies? Yeah, this diagram. So I wonder how the strengths. Well, this is still the merging, quite close to the merging. in terms of the whole life of two-body encounters, right?
Yeah.
You say days, it means that the time scale is
Yeah, days.
just days,
Yeah.
just before the merging.
Yeah, right.
Okay. So quite close to the merging
Yeah.
phase,
Yeah.
merging stage. But I wonder how this strength of the wave compared to the peak one at the merging plunging phase. In other words, how weak the gravitational wave strain for encounters or burst signals. This is post-Newtonian calculations. So do you
Yeah.
have such estimation roughly?
Actually, it depends on the amplitude. Depends on
Uh-huh.
actually the amplitude depends on the pericenter distance,
Uh-huh.
and in this case, the major axis here and eccentricity like that, and it means for the 10 solar mass, its pericenter is almost 2,500 kilometer. And if we can change it's a geometrical units, it's almost less than 100 m. So actually it's hard to expect this. You can detecting this.
Probably.
Yeah.
In LIGO, it's in
Yeah,
the soul.
I think it's hard.
You know the sensitivity of Einstein telescope is about tens or two
Yeah.
tens better than the LIGO.
Yeah.
So if the strength is just 1/10 of the peak one, the merging case, it's detector.
Yeah,
in
yeah,
the
maybe.
Future
Yeah.
Einstein telescope.
Yeah.
Of course, this is single burst, so you need to consider more things, but essentially, I think it's possible. So I want to know how the strength changes in each evolution.
Yeah, actually, the amplitude almost same from here to around here. At the final stages, the amplitude increases very fast, very quickly.
All right.
Any other question?